Namaste. Welcome to this channel, Dr.ARM's Chemistry. Friends, we were discussing last time the enantiomers, and today we are going to see the measurement of optical activity or specific rotation. Measurement of specific rotation. So this is our 117th episode. So in order to understand the difference between enantiomers, we need to measure the difference between the two in terms of specific rotation. For this purpose, we have to determine first of all the angle of rotation by using polarimeter. So the instrument required here is a polarimeter, and this instrument help us to measure the specific or angle of rotation, which is then converted into specific angle of rotation considering the concentration of solution and length or path length of the solution. So here this specific angle, specific rotation is given by alpha d. Alpha d is specific rotation, and angle of rotation is called alpha. Is called alpha. Then we will see the equation by using which we can get this specific alpha d, that is specific rotation. So this alpha d is given by alpha upon concentration C into L. Here alpha, we have seen the angle of rotation measured by using the polarimeter. Then here this C is concentration of solution, in grams per centimeter, and this length is the path length. It is called path length. So it is the length of the polarimeter tube. Length of polarimeter tube in decimeter. So in this way we can calculate the specific rotation, that is alpha d. So for this we have to use the instrument. So we will see the diagram of the instrument called polarimeter. This instrument is very simple to be observed. So if you see, this is a polarimeter tube in which the solution is filled. So one end of this is packed with a polarizer, that is Nicholas prism. called polarizer, and this end is packed with also Nicholas prisms, which are called analyzers. In between the solution is there, and this solution is packed. Say this is the solution. This is a solution of a compound which is to be tested for measurement of optical activity. Now, there is a source of light. There is source of light which is passing through this polarimeter tube, and this is a monochromatic beam of radiation. The source is specially used as sodium vapor lamp. Sodium vapor lamp, in which there it is using D line of sodium. So it is a monochromatic beam. So this is monochromatic beam of radiation. Monochromatic beam of radiation which is passed through this tube. So it contains the radiations which are having some shape like this. So it is normal monochromatic beam of radiation. But after passing through this solution, the radiation passing through this is having in different pattern, like this. So this is the observed radiation. It is not of this type. So it depends, the radiation coming after this, passing through this, is changing the plane or plane polarized light. So when this monochromatic beam passes through this dipolar prism, it is converted into a plane polarized light. It is passing through this plane polarized light, and after this it is coming out through this analyzer, where it is analyzed and specific angle of rotation, the angle of rotation is detected here. So if the solution is optically active, if the solution in this polarimeter, so this is a polarimeter tube, if the solution is optically active, then only the plane of plane polarized light will be changed. Otherwise, it will remain unchanged, and in such case the solution is not optically active. Then here we are using here our eyes. Eyepiece to observe the rotation. So here we can observe the angle of rotation, that is alpha. So this is about the instrumentation we are observed in actual case. This will give us the alpha d, that is specific angle of rotation, from our calculation as we have seen in earlier formulae. Now we will see some examples in which this experimental values are used to explain the difference between the enantiomers. So here light, as we have seen in this experiment, the light passing through the polarimeter tube is monochromatic beam of radiation. It is commonly sodium D line of the spectrum. In case, we can consider some examples. So for example, if we take the complex, that is pair of enantiomers, such as, that is delta and lambda of this complex chromium AC3, this acetyl acetone to chromium. So these two enantiomers, means optically active isomers, will differ on the basis of their interaction with the monochromatic beam of radiation in polarimeter. So the polarizer light, plane of plane polarizer light, whether it is changed or remains the same, and if it changes by what amount of alpha. So that will determine the fate of these enantiomers or optical isomers. The complex, such as CO En3 3+, this complex forms counter ion in solution when it is used for the determination of optical activity. It forms a counter ion and it results in the formation of the salt, and that salt contains the two types of chirality, that is indicated by delta and lambda. So at this metal center, such type of chirality is observed, and further, so these are the prefixes used to name or represent these optical isomers. If the signs, whether plus or minus, in this case also plus or minus, are given, if the angle of rotation is in clockwise or anti-clockwise, or plus or minus, that is the indication. Or in other words, D and L is also given. So in that case, these are the prefixes and these are the optical activities, that is angle of rotations. So on that basis, we can get the pairs of enantiomers, which are presented by this, say, delta plus and lambda minus, delta plus and lambda minus. Similarly, we can have, so this is one pair, that is of salt. Similarly, we can have delta minus and such lambda plus. So with this given anion chirality, the pair of salts, that is the the pair of salts, that is delta minus and lambda plus lambda minus are distereoisomers. These are distereoisomers. Distereoisomers. So which are not optically active, and they may differ in packing of ions. Means these are of same nature. Means they differ only the packing arrangement of their ions in solid state. Their separation is possible by fractional crystallization. Then if we take another example, so these are pair of enantiomers which are optically active. Now we will see the square planar complex, square planar complex and optical activity. So in this case, if we take the example of trans PdCl2 to MEPY, it is PD twice. So this is dichloro bis 2-methylpyridine palladium. So experimental fraction shows that environment of such compounds, and on that basis we can differentiate the structure of the isomers. So here PD2 unit, PD2 center is showing in this case the twisting of plane of benzene rings, that is pyridine rings. So such type of pyridine rings are twisted by about 18 degrees, so that even though the atoms are of same, the two species are there which are of the same nature, even though they differ in their spatial arrangement, so that the center of that is metal becomes chiral, and the twist of the plane of both rings, these are two rings of 2-methylpyridine. So the two rings are twisting by about 18.6 called the torsion angle. So we will see this diagram here. So if you observe this picture, you will find that the Cl are shown here as XX. Now these R R. R these, now depending upon this R can be changing. So here the R are the alkyl groups or aromatic structures, substituted structures. So this R can be here, R is equal to methyl group Me, that is CH3, Me, or we can see CH3, and R prime is hydrogen. Then positive torsion angle corresponds to P chirality. Now you will see that both the XX are same, means both CLs are same. So the structure is where we have to remember means this atom, these two atoms and this atom, both means all they are in the same plane, that is called a square plane structure. But now if we see, so we are showing this in order to understand the structure only. So if we mark these points, so this is A, this is B, this is C, and this is D. Then you will find that this AB and this CD are twisting. These are expected. ABCD is expected to be in one plane, but due to the steric strain between, steric repulsion between these two R groups, they are repelling each other and they are showing twist of this BCD. ABCD is twisted. It is twisting, so that the torsion angle is 18.6 degrees. Torsion angle is 18.60. So you have to remember that this torsion angle along this ABCD is this 18.60. So due to this torsion or twisting, the isomer, means these isomers are optically active, and in such case, so this benzene ring, which is expected to be in the same plane, it cannot remain in the same plane, that is, it cannot remain orthogonal to each other, but it gets twisted, and therefore this ABCD torsion is observed. When R is equal to this AB and R prime is equal to H, we find that the chirality of this structure is called the P. This is called the P chirality. P means plus. P means plus chirality. So with this we will stop our discussion. So please subscribe to this channel, press bell icon and like button. So thank you very much for watching this video.